Okay, so we've got kind of 4 topics here to talk about in this part of lesson 1.2. Our first topic is continuity. Being able to decide if a function is continuous or not. Okay, so if something is continuous, we say it has continuity. A function is continuous. Here's my easy description. If I can put my writing utensil down and draw it without ever having to pick my utensil up, it's continuous. I didn't have to stop, pick my pencil up, move it over an asymptote. I didn't have to stop, move it over a hole. There was no breaks in it. So if it's continuous, you can draw it all in one fell swoop, no stops, no breaks. Officially, if a function is continuous, that means there are no holes, breaks, or asymptotes. The big things we'll be looking at are the holes and asymptotes. So, if it's continuous, or in order for it to be continuous, we check for holes and asymptotes. Now, we did a little bit of this in Algebra 2 last year. We talked about holes and asymptotes. And this all comes down to the denominator. Okay? So, whether we're talking holes or asymptote, it's always about setting the denominator equal to 0. The key is if it's a hole, whatever's in the denominator will also cancel in the numerator. If it's an asymptote, there's no canceling. So, let's see, how do I want to do this? First thing, let's not do that yet. Let's take a moment and let's practice our factoring skills that you guys are pros at and you remember perfectly. X squared minus 4 over x plus 2. I probably should start off with the question, does it factor? Yes. And obviously, by the way I've let in, it does. Does x squared minus 4 factor? Yes. How does x squared minus 4 factor?
X plus 2 minus 2.
Does that sound familiar?
Yes.
It's the difference of squares. 2 parentheses. X squared breaks into x times x. The square root of 4 is 2. If it multiplies to be minus 4, we're going to say plus and minus 2. The denominator of x plus 2, does it factor? No. X plus 2 just stays x plus 2. What do you notice? There's an x plus 2 factor that can cancel. So after canceling, we're realizing when we set that denominator equal to 0, because that denominator had something it canceled with, it's going to make a hole. If there was no other x plus 2, it would be an asymptote. So I'm going to set my denominator equal to 0, which is x plus 2 equals 0. If I solve that, if it's x plus 2, we of course want to subtract 2. And then x equals negative 2. Now technically, since that's the denominator, that means x cannot equal negative 2. This is going to be an example of a hole. There's a hole at x equals negative 2. I know it's a hole because we were able to cancel the x plus 2. Now, I'm going to come back over here before I forget. Denominator equal to 0 is going to be a key thing to always remember to do. And then, besides doing what we did here, we can also investigate graphically. And we're going to practice that a little bit too. Now, when I punch this in, notice I'm punching in the whole thing before any simplifying happened. Okay. What do you notice about this graph?
It's a line.
It's a line. Does it appear to be continuous?
Yes.
Okay, it appears to be continuous. And this is why I was talking yesterday how I like to use my graphing and my algebra skills together. This is why, because if I just look at this graph, okay, it's a line. It's continuous. However, it's not. And the key is, where did we say there's going to be a hole? There's a hole at -2. If I hit trace, and I go over here, is it going to work? I probably can't get exactly, no. Okay, so it jumps over -2, yes? But if I hit trace, and I type in -2, guess what? -2? There's no y. That tells you it's a hole. Would you have gotten that just by looking at the graph?
No.
No. If you know to check -2, that's the key. And we knew because denominator equal to 0. Now, if you try and zoom in, I'm curious. Sometimes when you zoom in, you can see the hole. And it doesn't appear it's going to let me. But that's the thing. I'm zooming in, and I still can't see that hole. Sometimes it will show on the graph. This one is not showing. And so that's why it's so important that you use the algebra also, setting that denominator equal to 0. Okay? Okay, so that was an example of a hole. A hole is what we call a removable discontinuity. Okay, it's a removable discontinuity. Oops, I'm zoomed in a little bit. Let me zoom back out some. I like to think it's a removable discontinuity. It's something that can just, like a hole, it's a hole that can be plugged. So you can remove the plug, you can put the plug back in. Okay, it's a fixable discontinuity. You have to figure out a way that you remember which one's which. But a hole is a removable discontinuity. So we would say there's a removable discontinuity at x equals -2 because that's where the hole is. Okay. Asymptote. Same process in that, first of all, does anything factor? Does anything factor here? No, nothing factors. So, same thing as above, set the denominator equal to 0. So if I set my denominator equal to 0, what is this denominator? X minus 2 equals 0. So if we solve that, we're going to get x equals 3. Because this is the denominator equal to 0, this means my graph can't exist at x equals 3. Now, difference from last time. There's an x minus 3 in the denominator. Is there an x minus 3 in the numerator it can cancel with? No. So this time, it's not going to be a hole. It's going to be a vertical asymptote. Okay? And this is called a non-removable discontinuity. Okay? It's a non-removable discontinuity. I don't know, I think of an asymptote, it's not fixable. It's a big old break in the line. If I show this to you, where are we expecting this to happen at? 3. Definitely not continuous, right? Definitely a discontinuity, because there's definitely a big old break in the graph. Where are we guessing that vertical asymptote is? At 3. And if you count over 1, 2, 3, you can kind of think, does that make sense?
Yep.
Yeah? If I do some tracing, watch my x values. From this side, my x values are going to get closer to 3. Whoops. 2.87, and I'm way down at negative 73. I go one more. Now I'm on the other side of 3, but notice I'm way up at 298. So at some point, you know, it jumps from down there to up there because that's next at x value. Okay, so you can watch that on the calculator that, okay, I get all the way up here. I'm almost at 3. There's my last positive y value. Now I'm on the other side of 3, but I'm way down below the screen instead of above the screen. Okay? So questions there. Got the idea? Okay. Let's look at these two examples about asymptotes and holes. I should say discontinuities, sorry. Determine where the function has a discontinuity. It says determine where, and then state whether it's removable or non-removable. So how are we going to determine where this has a discontinuity?
Well, first we need to have a denominator.
Right, take the denominator and
Set equal to 0.
set equal to 0. So my denominator here is x plus 3 equals 0. You solve that. We're going to have
X does not equal -3.
right, x cannot equal negative 3. So there is some type of discontinuity at x equals negative 3. The question, is it a removable discontinuity, meaning it's a hole, or is it a non-removable discontinuity, meaning it's an asymptote? How do we decide? Okay. A, ask yourself if the top can factor. And then what's the other thing we can also do? Check the graph. Now, let's talk about the factor. Does x cubed plus 27 factor? Do we remember how to factor it? Okay, so let's see if we remember this. X cubed plus 27. I'm trying to remember. Did I teach this chapter P, or was this last year? Okay. So this is sum of cubes. So this factors into a binomial and then a trinomial. So the binomial is just the cube roots. What is the cube root of x cubed? X. What is the cube root of 27? 3. Because 3 times 3 times 3 is 27. Because there's a plus sign in the original problem, what goes here? Plus. Now, the next part is a trinomial. The first part of the trinomial is the first cube root squared. So my first cube root was x. When I square that, it is x squared. My middle part is these two cube roots multiplied together. So 3 times x, which is 3x, and then opposite this sign. So minus 3x. And then the last one is adding the other cube root and square it. So 3 squared is 9. So add 9. Now, that benefited me because what just happened? X plus 3 can cancel with x plus 3. So what kind of discontinuity is this at negative 3? It's a removable discontinuity. Or in other words, it is a hole. So removable discontinuity. Sorry, that one's hard for me to spell. At x equals negative 3. So we answered the question, where does it have a discontinuity? And that discontinuity was at negative 3. And then we also stated that it is removable. Okay, real quick. If we looked at the graph, you may or may not be able to even see that break in the graph because it's a hole. Let's look at B. Does that numerator factor on B? It does. X squared is x and x. What multiplies to be 2 and adds to be 3?
2 and 1.
2 and 1, plus and plus. Do any factors cancel? No. I have an x minus 2. Do I have an x minus 2 on top?
No.
No. Set your denominator, what?
Equal to 0.
Equal to 0. You solve that, you're going to get x equals 2. So x cannot equal 2. Is this going to be removable or non-removable? This is going to be an asymptote because it was not able to cancel, so it is non-removable. So non-removable discontinuity at x equals 2. Okay. Tomorrow, I will finish the front and back of this page, and that will put you on track for the 22 through 46. Okay? You might be able to do the first couple of problems, whichever ones talk about continuity. 22 and 24. You can do the first 2 problems. So not a whole lot.
He's like, check the public in Russia or not.